Welcome to hash tables. A hash function turns a key into an array slot, so you can find a value almost instantly. When two keys land in the same slot, we handle it with chaining or open addressing. The load factor tells us how full the table is, and rehashing keeps it fast. Let's start with why we need hash tables. We want to find a value by its key as fast as an array finds a value by its index. Hashing turns find this key into compute where it lives. By the end of this chapter, you will be able to do 5 things with hash tables. First, you can compute a bucket. You apply hash of key mod m to place a key by hand. Second, you can trace a collision. You follow a chain or a linear probe sequence until you reach the key. Third, you can decide when to rehash. You watch the load factor alpha, and you grow the table before it slows down. Fourth, you can implement both families in C, separate chaining and open addressing. Fifth, you can avoid the tombstone bug. You can explain why deleting a key must not just clear its slot. This chapter has one main idea. A good hash function turns a key into an array index. So a lookup does not have to search or compare its way through the whole structure. It computes where to look, the same way an array computes an address from an index. Everything else in this chapter is about handling what happens when two keys compute the same place. In a context app, a dictionary, or a compiler symbol table, you always arrive holding a key. A key is a name or a word. You want the value that is filed under it. This is an array of 5 fruit names. An array is instant when you already know the index. But you are holding the key cherry, not a number. You do not know which cell cherry is in. So which cell is it? You cannot answer without checking the cells one by one. An array gives big O of 1 access, but only if you already know the integer index. You arrive with a key, not an index. This chapter closes that gap. Let's try the obvious ways to find a value by its key. Both of them hurt. The first way is to scan the array, cell by cell, until the key matches. That costs big O of n with 1,000,000 keys. One lookup can take up to 1,000,000 comparisons on every lookup. The second way is to keep the array sorted, then binary search the key. The search is fast, big O of log n, but every insert slides the later keys over to stay sorted. So each insert costs big O of n. Scanning makes every search slow. Sorting speeds up the search but makes every insert slow. A balanced tree from chapter 11 also gives only big O of log n, and it keeps an order that a pure lookup never uses. The gap is still open. We want lookup by any key, even a string, as fast as an array is by index. Neither scanning nor sorting gets there. 2 everyday systems never search at all. They compute where an item goes, straight from the item itself. The first is a code check with computed hooks. Your hook number is computed from your ticket. You walk straight to hook H of ticket. You never scan the racks. The second is a supermarket Find My Item app. It computes the aisle from the product name. You go straight to that aisle. You never walk every aisle. Instead of searching for where a key lives, you compute it. A hash table does exactly this, with numbers. A hash function turns the key straight into an array index. That gives big O of 1 array access for any key.